Okay, so just for the video's sake, I'll just say we had this as a tuning in activity where you had to graph f of x equals e to the x and state the domain and range. Don't know if you did that or not. I actually looked at the graphs. I didn't look at the domain and range there. And on the same axes, graph f of the inverse of f inverse of x, and state its domain and range. So if I just zoom out now, there's the graph there on the top right-hand side there. So you can see that you should have had asymptotes in, and then we've got the lines, and you should have labelled the lines as well. Remember how I said that last time? If you're graphing two lines on the same axis, then you need to label your lines. I've colour-coded mine as well, but nevertheless. I might just zoom up so you can see that in a little bit more detail. What you should have been able to do is do the exponential graph like so, because that shape does not change, right? Whether the base is 2 or 10 or e, the shape does not change. It goes through 0, 1, because when x equals 0, e to the power of 0 is equal to 1. Even if you don't know that e is equal to 2.7 something, you should be able to put in that critical point, okay? Because anything to the power of 0 is just 1. There's one more point I've got here to give it scale as well, because it's an easy one. When x equals 1, what does y equal? Well, it will equal e to the 1. So that's just 1 comma e then. Again, know in the back of your head, that's about 2.7. It's about 2.7, okay? But you would write it as 1 comma e. All righty? And then we flip it. So the easiest thing in the world to flip is an asymptote. So particularly one which is just y equals 0. So that gets flipped and it becomes x equals 0, this red line here. So there's the flip. And then this line here is effectively a mirror of this line here. That's how it works, remember, across the diagonal. So this line here flips along 0 without even knowing what the inverse is. But 0, 1 would flip to 1, 0. That's why I've got that there. And 1, e would flip to e, 1, right? So our knowledge of inverses should take over at this point. And we know that an inverse effectively flips across y equals x. It's the mirror image in the way it looks. And the x and the y coordinates flip over. Every function has its inverse, but not every inverse is a function. Is this an inverse function or just an inverse? It is an inverse function because it passes the vertical line test. In order for a function to have an inverse function, it must pass the vertical line test because it's a function and the, exactly, horizontal line test. Excellent. So because this function here, the blue one, passes both of those tests, it will have an inverse function, and there it is mapped there. Any questions about that? Cool. I've got it on Desmos for what it's worth. Oops, wrong one. So I've just got a to the x here, and I've got a equal to 2, but it didn't matter, right? I could have made a equal to e, and it's going to be basically the same shape. There's the value of e for the rowers, 2.7182821828846, ... Goes on forever. So that's what a is. And yeah, no, it's not going to give us e in the thing. Sometimes it gives us exacts. So I'll just make it back to 2 just for the sake of illustration, but we've got this reflection happening. And you can see here that we've got log base a of x would be the inverse function, right? Because we know that the natural inverse of an exponential function is a log. So if it's log base 2, if it's 2 to the power of x, its inverse is log base 2. If it was 3 to the power of x, its inverse is log base 3. So if it's e to the power of x, what's its inverse? Log base what? Seriously, if you can't answer this, you're in the wrong classroom. If it's e to the power of x, its inverse will be log base e. Okay? So in other words, log base 2.7, blah, 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 blah. Again, just keep in mind what the value of e stands for. Don't stress too much about it until you've watched the video, rowers, but do make sure you watch the video from Friday. And anyone else who was sick, but I think it was just rowers. Everyone else is here, I think. So zooming out, I might go to slide 4 first, then go back to slide 3. So with slide 4, what is F inverse of X? Now this will test everybody. I could write log base E of X, but those are here on Friday. How do I write log base E? ln, well done, okay? So I always do mine as chord cursive so it doesn't look like one N. You don't have to do it in chord cursive unless you'd like to. So F, the inverse of X is L, N, X, okay? And you can put a note to yourself to remind yourself that's log base E of X. By the way, you will find in textbooks and all over the place really in tests and stuff, they will often not put brackets around the X. They'll just go log base EX or lnx without the brackets. Because it's such a common function, it sort of takes on its own life and it doesn't have brackets. Sine, cosine, and tan are also examples of that. I tend to put brackets in most of the time because I want to reinforce to you that it is a function. It works just like a function. So I'll do brackets for most of the time, but you might not see it all of the time. Okay, I should be able to pick on people for slide 3 there. The domain of F. The nice thing about having a graph is that you don't have to think too hard about it. Look at the graph and see what it's telling you. The domain of F, remember, is Dixroy, is the inputs, it's the X coordinates. What is the domain of F? Amelia, can I pick on you? Go. Yeah. Good. Excellent. X is a member of all real numbers. I'm just going to, I think I said before, I'll just settle on set notation for the sake of, but what you said was perfect. All real numbers would be from negative infinity to infinity. Well done. Who else? Lucy, can I pick on you for the range? Go on then. Yeah, or all real positive numbers because 0 is not positive. Yeah, excellent. Well done. Again, in interval notation, that's from 0 to infinity. How's that? Is that all right? What's the domain of its inverse? Shaker, can I pick on you? 0 to infinity. That matches the diagram, doesn't it? The domain is there's no x coordinates before the y-axis. There's an asymptote at the y-axis. So it must be all values from 0 onwards, not including 0. Well done. And Sunny, can I pick on you for the range? Beautiful. From negative infinity to infinity. And unsurprisingly for an inverse function, this range matches this domain and the function's range matches the inverse function's domain. And that's how it needs to be for an inverse, right? Otherwise, we're going to have gaps in our function or it's just not going to work out for us. Okay, so the inverse function is basically a logarithm function, but it has a special base E. Any questions before I move on? Speak now or forever hold your peace. Okay, skipping on. I'll just zoom up for the time being. So an important result. Do you remember that one from our composite function work and our inverse function work, sorry? F composed with F inverse is going to be, of X, is going to equal X. Okay, in other words, you don't have to write this down, but if I go F of inverse of X, I'm just going to get X out because the domains and ranges match up with inverse functions as usual. So that is always the case. Since that's true though, since F composite F inverse of X is always equal to X, then we can say the following things. We can say that the natural log, roll people, log base E is called the natural log. That's why it's ln, log, natural log. Why it's called the natural logarithm, you can watch the video to see why. So when you hear me say the natural log, I mean log base E. The natural log of of e to the x is equal to x. And e to the natural log of x is also equal to x. Two important results. Okay, so crassly, we say that ln and e cancels each other out. So this ln and this e cancels out, or this ln and this e cancels it out. Okay, so these cancel each other out, leaving with the x. But a little bit more refined is to understand that what we're doing is we're taking one function and we're applying it to the inverse, or vice versa. Its inverse is being applied to the function. So as always, the function effectively will output x. Whatever you put in is what will come out. Okay, so here's a simple example, and then I'll do a couple more examples and I'll get you to do some work. So solve for x e to the power of 3x equals 2. So what we effectively do, now I'm going to literally write this out, but you're going to find I do less literal writing as I go along. What I literally do is I am taking the ln of both sides. I'm taking the natural log of both sides. On the left-hand side, the ln and the e cancels out. That leaves me with just 3x. On the right-hand side, I don't evaluate. I leave it as the exact value ln2. I then divide both sides by 3, and I get 1/3 ln2. And that is an exact value. Okay, if I then evaluated ln2 and multiplied it by 1/3 or divided by 3, that would give me the approximate value, in which case you'd give it to 3 decimal places or 4 significant figures, whatever sort of makes sense for the context. But we tend to only do that if it's an application problem. Example 2, effectively, with all of these kinds of examples where you need to basically get at the x, which is inside either the log function in this case, or whether it's, as a power of e, what you have to do is you have to reduce it down to a single log, and then you can apply that sort of inverse principle. So ln 2x plus 1 minus ln x minus 1 equals 4. How can I convert that into a single log? Good one, Tian. He said log laws. Which one's going to help us here? Log A minus log B. Well done again, Tian. Log A over B. So in this case, we would do the following. Okay, you see what I did there? Just use that log law. So you need to know your log law so that you can do this without any dramas. Now the rest of it is relatively straightforward. I'm going to take e to the for both sides. So effectively what I'm doing, maybe I'll just do it for this example too, but I don't tend to do this. I'm going to go e to the ln of 2x plus 1 over x minus 1 equals e to the 4. And that means that 2x plus 1 over x minus 1 equals e to the 4. So what I'm trying to say is that I tend to go from this expression here straight to this expression here. I don't tend to do this. I'm doing it for the note so that you can sort of see that all I'm doing is I'm raising each side e to the power of. And it will be equivalent. Okay, so this is an equivalent equation. Okay, now I'll just finish off the problem. It takes a few steps, but it's kind of no more difficult than what we've been doing over the last couple of years, really. It just looks more complicated. So I've got 2x plus 1 is equal to e to the power of 4 outside of x minus 1. See what I did there? Just multiply both sides by x minus 1. Keep going. I need to isolate the x. That means I need to do whatever I can to get x onto one side of the equation and anything that's nothing to do with x on the other side. So all I can do there really is to expand here, e to the 4x minus e to the 4. Now, what I think I'll do is I'll add e to the 4 to both sides and subtract 2x from both sides. So I'm gathering my x's on one side of the equation. So I've got 1 plus e to the 4 is equal to e to the 4x minus 2x. Because I've gathered my x's in one location, I can now take x out as a common factor. And I'm going to switch sides as well because I'm a left to right reader. I tend to put the thing I'm looking for on the left. So I'm going to have x outside of e to the 4 minus 2 is equal to, and I'm just going to lead with the e to the 4 as well, e to the 4 plus 1. Is that making sense? So I've just taken out a common factor of x. I also switched sides. That's all I did. Switch sides and took out a common factor of x. And so x is equal to e to the power of 4 plus 1 over e to the power of 4 minus 2. And that is an exact answer. And I guess that's what makes this different from maybe a problem with a numerical base, like 2 to the power of 4. You'd evaluate that to 16, right? And so you'd end up with a single number at the end. But this is what you do with Euler's number. You leave it in e to the power of form or ln form for an exact answer. I need to switch screens to give you one more example, so I'll give you a moment to write that down and to ask questions if you've got any. Okay, so example 3, ln x minus 1 plus ln x plus 1 equals 1. So this log law is going to be log A plus log B equals log AB. Well done. So the next line of this will be ln, two sets of brackets here, x minus 1 times x plus 1 is equal to 1. Now, I tend to simplify as I go along. So I'll be looking at that and going, oh, wait, that's just starts with D, ends in dots. It's a dots, right? So I'm going to simplify that straight up to x squared minus 1. And that makes me feel happier anyway. Now I'm going to go e to the power of on both sides, but I'm not going to write it down this time. So e to the power of both sides will give me x squared minus 1 equals e to the power of 1, right? And again, raising to the power of 1, 1 is an implicit power. We don't need to write it down. It is implied to be 1 if it's not there. So we just write x squared minus 1 equals e. Sonny? For what, sorry? Which bit? From there to there? All I did is I took e to the power of on this side, just like I did in this example here. I took e to the power on both sides. So that cancels out the e and the ln. And that leaves me with just the inside, x squared minus 1. And then e to the power of 1 is just e. So it's not a formula. It's just using that inverse property that I showed you before. Because have a look at the screen, it cancels out ln because of the following properties. Because these are inverses of each other, if I take the natural log of e to the x, I'll just get x, whatever x is. So in this case, x is x squared minus 1, right? So ln of e to the x squared minus 1 would be x squared minus 1. Conversely, e to the power of ln x squared minus 1 is going to be e to the power of x squared minus 1. Okay? That's basically what it means. All right, so I've taken e to the power of on both sides, and that's why I've got the left-hand side as just x squared minus 1, and the right-hand side is equal to e. I've cancelled out the ln effectively. Now I'm just going to finish solving. X squared equals e plus 1. That little muttering that's going on whilst I'm talking is a bit rude. I say a bit. I say a bit, but I mean quite rude. Yeah. The polite thing to do would be to be quiet so that I'm not put off with my teaching and that people around you are not put off with their learning. That would be the polite thing to do. I think. Maybe I'm wrong. Happy to have an argument about it later if you disagree. So x is going to be plus or minus e plus 1, technically. But x can't be negative root e plus 1, right? So that means x is equal to the square root of e plus 1. Why? Because x, what? technically it can't be negative, you're right, but it's more than that. Have a look at the original equation here. Use the original equation, and do this with functions as well. Use the original equation to determine what x can or cannot be. Alex? Or 0. Okay, so if we look here, even if x was a half, we'd be in trouble. Okay, so we need to state that x is greater than not 0, but 1. Okay, for the reasons I just said. Hope that makes sense. All right, it is now 2:15. I've still got one more thing I need to show you, but I want to give you a short practice time first. So for the next 10 minutes, you're going to work from 5D and 5E. It is on the learning schedule which ones you have to do. I'll show you, I'll pause the video and then show. And although this is the last concept, it really is stuff that you've seen before, but we're just applying it to this new base E. So I've got an example here, f of x equals 2e to the power of x plus 1 minus 1. And you need to, I haven't written this down, but you need to find the inverse and state the domain and range of the inverse. So we start off as usual by changing f of x to y equals 2e to the x plus 1 minus 1. So we've gone from a function rule to the y coordinate is found by this rule here. And then as usual for inverses, we simply switch the y and the x over. We don't have to stress about, oh, does the inverse exist and all that kind of stuff, because we've already seen that, right? We've already seen that any exponential function will have a well-behaved inverse function. So I switch the inputs and the outputs in one fell swoop. And now I solve for y, which is what you've just been practicing and why I got you to practice that. So to solve for y, I need to get e to the all by itself, and then I can flip it over. So I'm going to add 1 to both sides. And I will have 2e to the power of y plus 1 is equal to x plus 1. So I've just added 1 to both sides there. Then I'm going to divide both sides by 2. And for reasons that will become clearer later on, I'm going to express it like this. E to the power of y plus 1 is equal to a half, that's a dodgy half x plus 1. So rather than divide through by 2, or rather than putting x plus 1 all over 2, I'm going to just leave it as a half outside of x plus 1. And it's because I know where I'm headed. Now I'm going to take the natural log of both sides. So ln of e cancels out, leaves me with y plus 1. Ln of that expression doesn't cancel out. I'm just left with ln of a half outside of x plus 1, like so. And finally, I'm going to finish off with y is equal to ln a half x plus 1. And to put it in the correct terminology, I now will go f inverse of x is equal to ln a half x plus 1 minus 1. So I didn't put the minus 1 on before. Okay, now it's the reason why I left it in this format, like a half outside of x plus 1, is because I know that I'm doing function work, right? And when I've got a dilation of the x, if I can take that out as a factor, I know that what I'm left with on the inside will be the translation. Okay, so I can see from this form here directly, I've got a dilation of factor of a half, but importantly, I've got a translation of 1 unit to the left and a translation of 1 unit down. So now I'm not going to do a proper sketch. It didn't ask me for a sketch, and I'm not doing one, but I'm just doing a quick sketch. I know that the graph, what a logarithm graph looks like. So I just quickly draw this. I know that it's going to be over here, and like that, that's going to be x equal to a half. Just a really rough graph, so I can sort of see what's happening simply so I can state the domain and range with confidence. That's all I'm doing it for. Okay, it's not a proper sketch. I haven't worked out the y-intercept, don't care. Haven't worked out the x-intercept, don't care. I'm really just getting a sense of what the domain and range would be. And I hope you can see that the domain is going to be not minus a half, sorry, x equals minus 1. So the domain is going to be minus 1 to infinity without including minus 1, and the range is going to be all real values. So from minus infinity to infinity. And that's basically it, team. So exercise 5H, which is in the learning schedule, has a few problems for you to try. The first set basically says find the inverse, find the domain and range of the inverse. And then a few more just gives you more practice of flipping the x's and the y's over a bit. So do as much practice as you can, but that is about it. So you've got about just under 10 minutes left in the lesson to about 8 minutes left in the lesson to practice those. And then you've got revision tomorrow's lesson is just revision. So you can keep on working on these or anything else in the unit.